So group 1 that we just drew all those graphs for, I want you to notice that they were always an x squared graph on top divided by an x, or a parabola over a line. Did you notice each of them had an x squared on the top and an x on the bottom? And when that happens, when you have a parabola on the top and a line on the bottom, we have one of two things happening. So the characteristics, we either have one, a hole in the graph, or two, a vertical asymptote and here's a new word for you, a diagonal asymptote called an oblique asymptote. So we're going to have either a hole in our graph or a vertical asymptote and a diagonal asymptote. Question? Characteristics. Yes, that looks like, but let's see. Does the computer like me? I'm going to find out here in a second. Just a little test. See if the computer likes me or not. No. Characteristics is close. So it was supposed to say characteristics. That's close. Characters. Okay. So it either has a hole, and watch what happens. We are going to discover why something has a hole. One of the main skills that you need for mathematics is factoring. If you took this first one and factored the top, you would get x plus 1, x minus 1. And on the bottom we have an x plus 1. And from your identities unit, you know you can simplify things. What could cancel out? The x plus 1. Which means your equation just simplifies to y equals x minus 1. Do you know how to graph y equals x minus 1? Yes, y equals mx plus b. It would have a y-intercept at -1 and a slope of 1. That's the line that we drew. However, -1 is still a non-permissible value in the original equation. So you draw the line, y equals x minus 1, but you have to include a hole in the line where the non-permissible value was. Exactly where is this hole? Well, what would happen if you plugged in -1 into the simplified equation? You would get as a y value -2. Yes? A non-permissible value you cannot divide by 0. We're dividing what value of x would make you divide by 0 minus 1. So let's look at the other ones that had holes. Second one had a hole. Could we factor it? It factors to x plus 2, x minus 1. And then your x plus 2's cancel out. And you're just left with x minus 1. Exactly the same graph as the first one, except this one has a hole at -2. And if we plug in -2 into this simplified equation, you get -2, -3. So again, the non-permissible value, because in the original equation, that's the number that would make you divide by 0. And finally, the last one, in the top, there's a common factor. You could factor out a 2x, leaving you with x minus 2 over x minus 2. The x minus 2's would cancel, leaving us with a hole at 2, comma, well, the equation that you're left with, after it simplifies, is just y equals 2x. Now if I plug in positive 2 in for x, I would get 4 for y. So that's how we find the holes. holes will appear if a non-permissible value cancels out and goes away. It no longer affects the graph because it's gone, but it's still a non-permissible value, so we have to add a hole to show that it was there. When you cannot factor, see these two here? I mean, this one I can factor, but it's x plus 1 over x plus 2, and nothing simplifies. When your non-permissible value doesn't simplify, it will always stay as a vertical asymptote. And when we look at this more in depth, we will also be able to find the equation for the diagonal asymptote. But we're not worried about that yet. We're just saying group 1, when you have a parabola on the top and a line on the bottom, two possibilities will happen. Either a factor cancels out and you get a hole, or it doesn't cancel out and you're left with a vertical asymptote. Next group. Take out Desmos. Group 2. Do you see that you either have a line over a line or a parabola over a parabola? We would describe this as the same degree on the top and the same degree. Do you remember the word degree from grade 9 math? That's the exponent. And x has a degree of 1. X squared has a degree of 2. Cubics have a degree of 3. So if there's the same degree on the top and the bottom, what happens? That's how you did, and on your graphs, I'd like you to draw a dotted line there for an asymptote, dotted line there. This one has a dotted line there for an asymptote, one there, and one there. Characteristics of this one is when you have a line over a line or a parabola over a parabola, you will have vertical asymptotes and horizontal asymptotes. Again, your non-permissible value on the bottom ends up being your vertical asymptotes. Some of these we're going to factor. So for example, in the second one, you could factor the top, x plus 1, x minus 1, and the bottom, x plus 2, x minus 2. And the last one, I guess you could factor out a common factor of -2 out of the top. Now, wherever you have non-permissible values, that's how you find your vertical asymptotes. Same as the vertical asymptotes in group 1. But how do we find the horizontal asymptotes? So this one's at 3, this one's at 1, this one's at -2. Horizontal asymptotes tell you what's happening when x is really, really big. Okay? I wanted you to do some estimation mental math if I give you a very big number. How big? Like 1 billion. What is 3 times 1 billion really close to? 3 billion? Okay. What is 1 billion minus 1 really close to? 1 billion. And if you had 3 billion divided by 1 billion, what would you be close to? divided by 1 million. You'd be really close to 3. There's your horizontal asymptote. Basically, what's happening is when x gets really, really big, the -1 doesn't really matter. Okay? What do you think the Amazon guy, what's his name? Bezos? Something.
I stole a dollar. I stole $1 something.
Would it make a big difference in his life? Right? Because when you have so much, losing $1 is like whatever, right? If all you had was the money to go home on the bus after school and you lost $1, it's a big deal, right? Now you can't go home. But if you have, when x gets really, really big, minusing 1 does not matter. Same thing here. As x gets really, really big, the +4 doesn't matter. The -1 doesn't matter. What is -2x over x? Simplifies -2. Here, if we ignore the small stuff, the biggest one is x squared over x squared. What does that simplify to? Just 1. So our horizontal asymptote is just looking at the biggest degree. In this case, it's x. 3x over x, that gives you 3. And this one, x squared over x squared, that gives you 1. And in this one, -2x over x, that gives you -2. So if they are the same degree on the top and the bottom, you end up getting a horizontal asymptote by just looking at the coefficients. All right, group 3. Group 3, we went from parabola over line, the degree bigger on the top, then the degree's the same, and now we're going to have the degree bigger on the bottom. So this could be a line over a parabola. The degree is bigger on the bottom. All right, on these ones, take out a red pen. So the degree is larger on the bottom. On these ones, the main characteristic is that the horizontal asymptote is always at y equals 0. As soon as you get a degree bigger on the bottom, you will have a horizontal asymptote at y equals 0. Notice that the first one doesn't have any non-permissible values. The second one, if you factored it, you would get non-permissible values of 3 and -1, and you get 2 vertical asymptotes there. And the last one has a non-permissible value at 0, and you have a vertical asymptote there. So we're going to learn that our non-permissible values are either holes or vertical asymptotes. We are going to learn that there are 2 groups that have horizontal asymptotes. If the degree is bigger on the bottom, that's the easy one. It's y equals 0. If the degree is the same on the top and the bottom, then it can be a whole bunch of different numbers. We just have to look at the largest degree on the top and the bottom and divide them. And then we're going to also find out how to find those diagonal asymptotes as well. So we just have to figure out how to graph each of these, and then this unit is over.